So now let's talk about the central limit theorem. Hopefully you've already watched the Bunnies and Dragons video, which is, I feel, a great introduction to the central limit theorem. But now let's talk about it in a little more detail. So again, we've just watched that great video that gave us a great visual of what the central limit theorem is. But essentially what it's saying is it doesn't matter the distribution of the population. And remember, the population is the larger group that we are studying. If we take a mean of our samples or proportion of samples, so sample mean or sample proportion, that is going to become approximately normal for a large N. So let me give you an example over here with my die. I'm assuming, and this is at 2,000 tosses, or more than 2,000 tosses, I've basically rolled the die almost 12,000 times. Okay. The distribution of the population is fairly uniform because I expect to roll a 1 and a 2 and a 3 and a 4 and a 5 and a 6 an equal number of times. So uniform distribution. However, what if I take 3 rolls and I find the average number that I got on those 3 rolls, and then I plotted that? And then I did that over and over and over again. So if I took the average of 3 die, and again, number of tosses, notice now it's not uniform because I'm not looking at the value of the die, I'm looking at the average, a mean value of the die. And if I then look at 20 die instead, so again, N is getting larger, then notice it's becoming more like the normal model, unimodal and symmetric. So this is outstanding. Why is it so important that we know this? Because what we're able to do is to say it doesn't matter what the population is, let's take a sample mean or sample proportion for a large N. Now all of a sudden we have the normal model. We can find z-scores, we can find probabilities using all of those things we've just reviewed how to do. And that's our goal, is to be able to take a sample that is representative of the population, and then we're going to make inferences. So this whole half of the course is called inferential statistics because we're going to draw conclusions about the population based on what we see in our samples. Now, before we get too pumped up about the fact that the central limit theorem is awesome, we have to look at our assumptions and conditions. And essentially what we're saying is we need our situation, parts of our situation, randomization, independence, etc., to be met. We need those conditions to be met in order for us to say that that sample is representative of the population. So first, we have to say that the sampling method is randomized. Well, we talked a lot about randomization and all of the different sampling methods. We really want this to be randomized because we want our sample to be a good representation of the population, because if it isn't, then I can't make inferences about the population from the sample. Independence assumption. Independence means that the result of one sample must be independent of another sample. So if I'm looking at each sample, do the results that I got in one sample, are they going to affect the results that I have in another sample? Again, we've talked a lot about independence and what that is. If they're not independent, then they're going to resemble each other too much, and it's going to distort all of our solutions, basically. Then there's the 10% condition, and that is saying our sample must be less than 10% of the population. So again, if my population were 100 people and I sampled 80 of them, that's not good because I've talked to too many people in the entire population. So if I had, say, 1,000 and I talked to 80, well then I could say, as long as those 80 were randomly selected, then yes, it's representative of the population. So less than 10% of the population, and then it's going to be one of these two, and that's going to be based on if we're dealing with means, which is averages, or proportions. So if I'm dealing with means, then I'm going to look right now at the large enough sample condition, And again, when we look further into detail in means, we're going to change that up once more. But for now, we're just saying, hey, we want our sample to be large enough so that our sample mean will represent the normal model. So the pictures that I showed you of the samples of dye, the larger n is, the more we're going to have a sample distribution that represents the normal model. So we're typically looking for n is greater than 30 or greater than or equal to 30, but if you create a histogram from the samples and it looks nearly normal, then you're okay. If you're dealing with proportions, so remember means I'm dealing with an average. So when I was dealing with my dice, I looked at the average value. If I'm dealing with a proportion, which means the percentage of time that something happens, we have to make sure we have at least 10 successes and 10 failures. And again, it's using the same idea just to make sure we have a large enough sample size.